So last time we looked at the beam on elastic foundation with distributed load. We went through this example. And y'all had a lot of good questions about this concept and how to interpret the various parameters. And so what I did, because I used to have this and then I lost some of my files, so I recreated in Excel just this example and plotted it. And I think I tried to open it in here, but it's going to be hard for me to maneuver, so I might switch over to my laptop for demonstrating certain things. But this is just what I put together to represent the example, and I plotted the moment and deflection starting at the left end of the beam. So it doesn't have the exact same plot as what we see in the notes here, right? So here I had the rough sketch of the maximum moment, or from the left end of the load, not the beam. Of course, it's an infinite beam, right? So from the left end of the load to the right, this is where I started the Excel plot and went beyond. So of course, it's mirrored on the other side as well. And we noted that the maximum moment here is going to be 1343 pound-inches with the values that we plugged in. And that will occur at 7.85 inches from the ends of the load on either side of the beam, or on either side of the end of the load distribution, right, within the beam. So going back to that, right, we can see that trend. Oops, that's not what I meant to do. You can see that trend plotted in the moment diagram. And then in the deflection plot, it does show a trend similar to what I was trying to sketch the other day in response to the moment, where it just kind of flattens out within the middle. The only difference is it's obviously not, right, zero. You have that magnitude that we calculated, and then towards the end of the beam where we calculated the deflection, it was like half of the value in the center, right? So we can see that trend when we plot it too. So this is what it looks like, where you just have a little bit of curvature at the very ends of the beam associated with where those moments are, and then it kind of flattens out. So how is this affected by different values? This is where I'm going to actually jump into the computer, because I don't want to mess with this on the internet app for Excel. So I'll fit this in. It has to go on this side. Bear with me. All right. And so here, all right, this is kind of what I'd also like to see in your plots with regard to homework 8. So just kind of plot the data points, don't mess with lines. For plotting this, I just set up, right, a standard increment for X. I picked every 3 inches, and then have the calculations here for beta times X, A and B, which are those parameters that measure from the point where you're calculating deflection to either end of the distributed load, and then so on. So here's the capital B evaluated at those two values, capital D evaluated at those two values, and then the formula for deflection and moment calculated here. So you can see the values match up with what we calculated in class. For X equals 0, the deflection at either end of the load is 0.4167 inches. The maximum moment occurred at 7.85 inches from the end of the load, and that's reflected throughout, right? Here's the maximum deflection at the 120 inches from the end of the load, and so on. And then beyond the load, right, some of the formulas change. So now you're dealing with D and E, and then your V of X and M of X values will change, or the formulas will change, right? And the values still check out to what we showed in class. So you still have that maximum moment magnitude at 7.85 inches from either end of the distributed load. And then what I really kind of wanted to demonstrate here is showing how some of these parameters will affect the results. So I'm not going to mess with the load at all because the load will only change the magnitude of the results. It won't change the behavior of the beam. If we just focus on beta first, right? So these are the values that were given in the example. We were looking at a beta of 0.1 per inch. So I wanted to kind of think about what would happen if we increase the stiffness of the foundation and the beam, like we were sort of talking about in class, because we talked about how these parameters that were given represent a relatively flexible beam on a soft foundation with significant load, right? Well, if you calculate that out, just for context, right, the EI we calculated was this value, and if you factor out, right, the magnitude of E, Young's modulus, for aluminum, which is roughly 10 times 10 to the 6, you end up with a moment of inertia of about 0.05 inches to the fourth, which is really small, right? And for steel, it's even smaller. So we're talking about a really small or really flexible material here. So I just kind of wanted to see what it would look like if you had a steel beam with a more normal moment of inertia. So I plugged in 30 inches to the fourth for a moment of inertia of a steel beam, and that's what your EI product would be. And then if I increase the foundation stiffness to 20,000 psi, our beta with those, so we're increasing the stiffness of both beam and foundation, but the beta decreases, right? So now beta is roughly 0.05. So if I just plug in 0.05 here, all right, and I have to update this value as well. The way that I set this up. So with 0.05, or actually no, I don't have to update that. So let's just look at the effect of strictly just changing beta, right, to represent that new ratio. With a beta of 0.05, that now represents a beam that has more stiffness relative to the foundation compared to before, right, the beta 0.1. So that change, and I'll demonstrate that again, you'll notice that the moment distribution is affected, right? So the magnitudes get larger, and also the length within the load distribution, or I guess the length of the beam in general, because you have outside the distribution as well, that has significant moment is increased, right? So there's more beam that has significant moment. And then as far as the deflection goes, how that, let's see, I guess that, to show it, maybe I'll bring that down here so we can see how that updates. All right, so that just kind of changes it a little bit. The magnitudes don't change significantly for the deflection, but the distribution of the deflections change a little bit. So what would really affect the deflection magnitudes is changing the value of the stiffness modulus of the foundation, right? So if I increase that to the 20,000 psi over here, now we have, roughly this magnitude of EI for our problem. The distribution of the deflections, right, the trend hasn't changed much, but the magnitude significantly decreased, right, which makes sense. So this just gives you an idea of how those different parameters can affect that. If we go back to the original 200 psi, 0.1, all right, so we've seen what happens if we decrease beta. If we increase it, that would represent a beam that is more flexible with respect to the foundation than what we looked at. So let's say we bring that, we double it, right, and bring it to 0.2. So the magnitude of the moment has decreased, and also the distance over which you have significant moment has also decreased within the beam, right? So this is sort of what we talked about in class, right? The larger beta becomes, the more flat you will get with your moment distribution within the beam and also your deflections, right? So I just kind of wanted to demonstrate that.
Is that displacement graph continuous, or is it just sharply jumped? Or is that?
So it is a sharp jump, right? Of course, over small magnitudes. So this is where the load would end.
Right.
So there would just kind of be like it would pop up a little bit because you'd have the foundation still pushing up on it, but the
Right.
load wouldn't be pushing down. Yeah. Yeah. So, I mean, technically it would be continuous because the beam is continuous, right? But just the way I plotted it, it looks discontinuous. Yeah. And also to plot that, to get it to look like downward deflection is down, I just negated the result from the V of x term, since our sign convention for this puts positive downward for deflection. Any other questions? Okay. All right, well, thanks for sticking with me through that. We'll shift over to finite element analysis now. All right. So get through the homework. All right. We're actually starting finite element analysis this week in my other class too. A little bit of a different approach. We're not going to go as in depth into the background, and we're actually taking a different approach. In this class, we're going to be coming from virtual work. So here, with finite element formulation, and I expect everyone's had a little bit of exposure to finite element analysis. Is that right? Okay. All right, so we have a complex structure, right, that's represented by discrete number of finite elements and nodes. That's your basic finite element definition. And each finite element approximately represents the behavior of the structure or the portion of the structure that it replaces. So one way that we can derive this is through virtual work, which is what we're going to apply in this class. All right, obviously within this mesh here you have any single area that's defined between nodes is your finite element. Right, where of course the nodes are the connection points between those elements. So that's just one example of a finite element mesh. In general, the more elements that you have defined, the more accurate your solution will be. But that also means it's going to be a more expensive process. It's going to take longer to analyze. And so the goal is to try and find a balance between efficiency and accuracy with these analyses. All right, so applying the principle of virtual work, we consider that an elastic material is in equilibrium if the total virtual work is 0 for any admissible displacement, as long as the forces are remaining constant, right? So write that down. So keywords here, if the virtual work is 0, then the elastic material is in equilibrium. So we can define potential energy by the expression shown below, where capital Pi is used to represent the potential energy. All right, so that's equal to internal energy, which is the capital U, minus work done by external forces, which is the capital W. With virtual work, we consider the increment or the variation in virtual displacement. So that increment is represented by a lowercase delta. And so we would just take the increment of this equation, all right? So delta pi is equal to delta U minus delta W. And that has to be equal to 0 for equilibrium. right, so that lowercase delta represents the variation in virtual displacement. So we'll demonstrate this concept with a simple linear spring. If you have, right, a spring with stiffness constant K, as shown here, we're going to track the motion of this point that I've labeled A. So if you apply a force, of course, that point will displace to the right as the spring stretches. So in that situation, the internal strain energy would be 1/2 kx squared. All right, so that's the potential energy of the spring, right? You all should be familiar with that equation. Now, if we assume a virtual displacement, and this is kind of just a thought experiment because a virtual displacement, this means it's imaginary. There's no force that's added to the system. All right, so we would say under a virtual displacement, that point would move an additional delta x, all right? We'll say virtual displacement of the spring. The internal strain energy would then be U plus delta U, or 1/2 K times the quantity x plus delta x squared. Carrying this out, that gives us 1/2 kx squared plus kx delta x plus 1/2 k times delta x squared. We eliminate the higher order virtual displacement term. And so we can conclude then that delta U is equal to kx times delta x. All right, since we've already established that U is 1/2 kx squared, it follows that delta U must be equal to the remainder of that expression.
How do we eliminate the higher order?
Just general, higher order of an imaginary small displacement, right? Negligible. So again, with virtual displacement, we've held the forces constant, right? So there was no increase in actual force to generate this virtual displacement. And the increment in work done would then be delta W, it's a funky delta, is equal to F, right? So F didn't change, times delta X. So going back to our virtual work expression, we would have the increment in potential energy is equal to delta U minus delta W, or kx minus f times delta x. And that has to be equal to 0 for equilibrium. So I'll just recap these terms. We had that as kx times delta x. This is f times delta x. And then with f being equal to kx, right, this works out to be 0. All right, so now talking about finite elements in the context of beam bending. In general, our goal is to apply this virtual work principle to be able to relate the nodal deflections. So that would be your transverse displacements and rotations at your nodes. We want to relate those nodal deflections to the corresponding nodal forces. So that would be, they're not shown here, right? But that would be your transverse forces at each node and moments at each node. Now, a couple things I want to add to this little sketch here. We've got this straight line is representing the original undeformed position of an element, right? It's with node 1 at the left and node 2 at the right. So under general forces, F1, M1, and F2, M2, you would end up with a displaced position and shape that looks something like this, right? And the other thing I'd like to note is that X is measured along the length of the element and will always be 0 for beams at the left end. So X equals 0 at node 1 and X equals L at node 2, where the total length of the element is L. And I'll reiterate the goal. All right, so just on the previous page, we demonstrated how we can relate that to a spring, right? A linear spring, which is probably the most basic and simple application. And now we're going to expand on that and apply it to beam bending. Since this is a little bit more complicated, we're going to start by assuming a form for the equation of deflected shape. So we'll represent the beam deflection by a polynomial expression where the lowercase a's will represent constants. And so we'll evaluate constants by applying boundary conditions. So in this generic setup, all right, we don't really have much information about a specific, any supports or anything like that, right? So we're just going to be very, very general in this initial derivation. So we're just going to say V at x equals 0 is equal to V1. That's your nodal displacement at node 1. The slope, dv dx, at x equals 0 is equal to theta 1, the rotation at node 1. And then similarly at node 2, v of L is equal to v2, and dv dx of L is equal to theta 2. And I already defined L above, but just to be clear, it's the length of the beam element between nodes. So sometimes we would represent a whole beam with multiple elements. So in that case, L would not be the length of the beam, it would just be the length of the element that you're considering. So here, of course, we have 4 equations to obtain 4 constants. All right, so I'm going to spare you the details of going through that process and finding the constants, and no, you won't have to do that in your homework either. So we'll just skip ahead to the results. Because all of this is derivation. We're just getting ourselves to a set of equations that we will then apply, right? You're not going to have to go through this process in your homework or on an exam. But you should understand where it comes from, which is why we're going through it in class. All right. So I'm just going to leave this at the top to make it clear that this is after we've found those constants. Oops. Well, sure, I'll keep it in orange. Why not? All right, so we'll have then in matrix form a row vector, so 1, x, x squared, and x cubed, multiplied by a constant matrix, which I'll define below, and a column vector, capital delta, to represent the displacements at the nodes. So this capital B is your constant matrix, which will always be square. And then this is your column vector. So I'm going to expand both of those below. So first up, that constant matrix. We'll have 1 over L cubed in front. And then in the first column, L cubed, 0, negative 3L, and 2. In the second column, 0, L squared, negative 2L, and 1. third column, 0, 0, 3L, and -2. And then fourth column, 0, 0, -L, and 1. And then the delta matrix will just be your nodal displacements in order, specifically V1, theta 1, V2, theta 2. So then if we multiply that matrix equation out, we end up with what's shown right here, right? And here you can see this is just an equation for the deflected shape of a single element between two nodes, right, where you have V1, there we go. All right, your nodal displacements are generally unknowns going into the problem, all right? And that's what you're solving for. Once you have solved for those unknowns using finite element formulation, all right, you can use this expression to calculate the deflected shape or the vertical deflection of the beam at any point along the length of a given element, right? Using the appropriate expression for that element. So this represents the generalized deflection equation. All right, and what you need to know in order to use this equation are the nodal deflections. And in order to get those nodal deflections, you go to your finite element solution. So I'll just note here the FE solution provides these values. And that's what we're going to get into below. All right, so now going back to strain energy. All right, for a beam in flexure, your internal strain energy is 1/2 times the integral of the normal stress times the normal strain over the volume. And of course, your normal stress is Young's modulus times normal strain. And normal strain is -y times the second derivative of deflection with respect to x, as we defined previously in the beam bending lecture. So putting this into our matrix equation above, all right, we have an expression that we wrote for v of x in matrix form. So we're just going to go ahead and take the second derivative of v of x to get an expression for our normal strain. So applying that to that row vector, that's just going to be negative y out front times 0, 0, 2, and 6x. Just taking the second derivative of each of those row vector elements from v of x. That will get multiplied by the constant matrix, right? And your deflection matrix. So I'll just note that is the second derivative of v of x. All right, so now getting back to the strain energy, because ultimately we want the strain energy in matrix form. We have capital U is equal to making our substitutions, right, into the expression we wrote above, Young's modulus over 2 times the integral of normal strain transposed times normal strain over the volume. So we can rewrite this then as the integral, a double integral, right? So where the first integral is over the length, so evaluated from 0 to L, and then the inside integral is over the area, and that would be the cross-sectional area of y squared. So applying the transpose of this equation, we would have first, right, the delta transpose, and then the B matrix transposed, and then that row vector transposed into a column vector. And then the untransposed expression for normal strain in X. So then that would be evaluated over the area and then over the length. And since we previously acknowledged that the integral over the area of y squared is equal to the moment of inertia, we can rewrite this expression for internal strain energy as 1/2 of delta transposed times the stiffness matrix K, which I'll define in a moment, times delta, all right, so this represents the internal strain energy of the beam. Where that stiffness matrix K, and I know this will look familiar to those of you that took my structures class, is EI over L cubed. And then this is going to be a 4x4 where the first column is 12, 6L, negative 12, 6L. Second column, 6L, 4L squared, negative 6L, 2L squared. Third column, negative 12, negative 6L, 12, negative 6L. Fourth column, 6L, 2L squared, negative 6L, 4L squared. So that was a long way to get there, right? Slightly different from how we approach it in Structures 1, but along the way, what we did differently, or one of the things we did differently, right, that is beneficial, is we obtained this expression that we can go back to and then calculate the full deflected shape of an element once we have solved for those nodal displacements. Question?
Yeah, I think I'm confused about where the strain transpose times the strain matrix times the transpose strain matrix is really coming from.
Okay, so we started off with this, right, and then we substitute in, so we have normal stress times strain is within the integral for evaluating strain energy.
Right.
If we substitute in Young's modulus times normal strain, we end up with normal strain times normal strain. But in order to make that operation happen in matrix form, we have to use a transpose. Yeah. Yeah. Good question. Any others? No? All right. Well, I think that's probably a good place to stop for today. Next time we'll just wrap up those thoughts and then start applying it to some simple beam bending problems. And then we'll pretty quickly escalate that into some more complex problems and scenarios. So, all right. Good deal. See you all on Wednesday.